The extra stack, there's way too many to, I don't know if there's too many to, here, there, and there, there's not enough. You do another two, and then you got enough there, you need one more, you guys need one, you need two, there's two, there's some extras, alright, oh yeah, I gave you way too many. There's one, you want one? Two. Does everyone have one now? Incredible. So good. Yeah. This is good. Let's stick the stack here for the people who don't want to give me their homework. I'll get it in a minute. Okay, so I've got the quiz here somewhere. Where did I put the quiz? There. Oh, there it is. Thing. Discard, keep, discard. Keep. One, two, three, four, five, six, seven. All right, I know you're all done. It was too easy. So pass it over. I know some of you are probably just putting your finishing touches on your quiz. That's fine. You know, you want to draw a little picture, that's fine too, but try to wrap it up. Yeah, send it over towards the middle here, and then I can evaluate, figure out if you're ready. This whole row. All set? Good job. I think I got them all. look at them all, and I noticed that you all have the same answer, as far as I could tell. And it's not the answer I had, so I don't know. Something's wrong. I must have done it wrong, is what I'm saying. We're going to find out here. It's always fun when that happens, because, like, there's either you I don't know. Let's find out. Let's see where I must have done it wrong. So let's see what I did wrong. Just a minute. Where's my thing here? Here we go. So, given my track record today, things are just falling off the wheels are falling off the bus. But is this correct? Did I get this one right? I hope so. Dot product. I got 1 times -3 is -3. 2 times 2 is 4. 3 times 1 is 3. So that one's right. Yeah. So that one. Yeah. That's not the one I'm talking about. It's the second one. And I'm like, wait a minute, everyone's getting this one number, and I didn't get that. Okay, so let's see if I went wrong. We'll find out. Okay, so the next thing, let's just do the work up here, and then we'll go down to my work. We have the magnitude of u is going to be the square root of 1 plus 4 plus 9. Is that right? 14. And then that's the same as the magnitude of v, ends up being the same thing because it's the same 3 numbers. So okay, so that's okay. So let's see, where is my work here? So the cosine of my angle should be the dot product over the square root of 14 times the square root of 14. Okay, and that's this. Okay, so far so good. Just a minute. Now maybe I punched it into my calculator wrong. Let me check. Yeah, my calculator's in radians, of course. I can't, yeah. I did something stupid. So, yeah, here's what I did on my calculator. I computed the cosine of 4. It's so dumb. Okay, so there's my answer, which is not right. So I should have done the inverse cosine. Okay, so let's try again. Let me do it. Inverse cosine of, how embarrassing, of 4/14 is 1.28. Okay, so here's the right answer. I'll put it over here. It's 1.28, which is what everyone got, radians. And that's the same as, let's see, multiply by 180 divided by pi. And that's the same as 73.4 degrees. 73.4 degrees. Okay, so there it is. Incredible. Normally, whenever I notice, I like you guys enough that I don't mind. But normally, if I notice, like if I was teaching, like when statistics, if I notice everyone's got an answer that I don't have, usually I just, quietly come up here and I'm like, oh, I wonder what and then I just fix it. No one knows. So, but you guys are, you get the benefit of, I like you, so you can see behind the curtain a little bit. Okay, so today, as I mentioned, some of you are bored because you've done this 5 times already. Is that right? Every single class has dot product. Sorry about that. So this will be a quick review. I'll try to be quick. And maybe what I could do is focus on the cool, I don't know, some of the cool things that in mathematics we might use these things for. So cross product. By the way, the reason why we're interested in this is because we're going to be talking about vector functions. And if you can imagine flying a spaceship up to the International Space Station, which we got to do that sooner or later to get the astronauts off who are stuck up there. But because Boeing blew it with their whatever capsule that they sent up there. But anyway, so we need to send a spaceship up there, and that spaceship is going to follow a path. That path is a vector function. And so we'll get to the definitions of that in a bit. We're also going to be interested in vector fields. So you can imagine like the flow of water through a pipe, and you've got a vector field and understanding how things work in that vector field. And I know you do this in fluid dynamics, but anyway, these are the basics so that we understand the stuff. So the idea, I won't make us suffer through this. Normally, if I had students who didn't know anything about cross product, I would present this as our sort of anticipatory set of like what sort of a, vector could you think of that is mutually orthogonal to both of these? And I know you know the answer if you know the cross product, but let me just explain. So just briefly, we won't do this in full, but usually what students will say is they'll say, well, what we need is we need to come up with a vector like this, where you can do the dot product of that with 1, 1, 1, 1, 1, 1, and get 0, because orthogonal means perpendicular. Sorry, I should have mentioned this. Someone asked me, what does orthogonal mean? It's perpendicular, orthogonal, perpendicular. It's a fancy word for perpendicular that we use when we talk about vectors being perpendicular. So if you have a right angle, the dot product will be 0. And you could set this up as an equation. This is going to be a plus b plus c should equal 0. And then if it's also perpendicular to this other vector, 1, negative 1, 1, then you end up with this, that a minus b plus c equals 0. And I realized that this isn't at all what you would do if you know about the cross product. But we could actually solve these two equations for 3 unknowns. Wait a minute. 2 equations, 3 unknowns? There is no solution. Well, no unique solution. But we could do this sort of thing, add these two together, and you get that, no, the b's cancel. 2a plus 2c equals 0, which means that a is equal to negative c, and b can be anything you want it to be. No, it can't. B has to be 0. B has to be 0, doesn't it, for this to work? So a vector, not every, there's a whole family of them, but one vector that works for this would be this, would be this vector. The vector, let's see, a is negative c, so 1, 0, negative 1. That is a vector that is perpendicular to both of these. Now, we're not going to do it this way, but like I said, this is what I would usually do with students who don't know about cross product. So let's talk cross product. Hold on a minute. What's going on here? Just a sec. I need to fix something. So I have to fix it over here, though, oddly enough. Is this it? Where is it? Yes, here it is. Just a sec. So just take a apply to all equations. Yes. Okay. This is going to make it smaller, but better. There. That's better. So in order to understand cross product, by the way, the whole business about cross product is that as a cross product, the cross product answers this question, is what vector is perpendicular to both of these? So when we do learn about the cross product, we will find a vector that is perpendicular to both of those. It also has some other interesting properties that we'll talk about. So I'll do this, I'll make it quick, but if those of you who don't know about the cross product, if you're confused at all, please let me know, stop me, slow me down. Otherwise, I'll blow ahead. So first of all, matrices. A matrix is just an array of numbers like this. If you've had linear algebra, you're probably very familiar with this. If you haven't had linear algebra, just think of this as being a table or an array of numbers. So I've got these labeled like this, but you could have any numbers you want, like this, 1, 2, 3, 1, negative 1, 0, 5, 7, 2. Something like this is a matrix. So that is a matrix of numbers, a grid, array of numbers. We're going to be interested in doing the determinant of this matrix, of this array of numbers. And once again, you don't have to know exactly what the determinant is. We're using it as a tool. It's a computational way of taking these numbers and crunching them together into a single number. So a determinant is kind of like a measure of a matrix. It determines something about the matrix. That's why we call it a determinant. But if you want to know what it determines, go take linear algebra. For us, we're just using it as a tool to compute the cross product. So to understand the determinant, what I'm going to do is I'm going to take that matrix and I'm going to append it. So I've got, here's the original matrix right here. And what I did here is I took the 2 columns, and we'll do this really in just a minute. So I took that column and I copied it over, and I took this column and copied it over. Now, some of you are thinking, I know how to do a determinant, and that's not the way I do a determinant. That's fine. I'm just showing it for the people who don't know. If you don't know how to do a determinant, this will be the easy way. It's kind of like it works for 3 by 3. This technique does not work for 4 by 4 matrices or beyond, but it works for 3 by 3 matrices. So a determinant, what we're going to do is we're going to take this matrix,
augment it with the first two columns, and then draw diagonals through the matrix. So let me draw my diagonals, and then we'll talk about what happens with the diagonals. So here is the down diagonals. There's that one, and there's that one. So there's three down diagonals. So you see those down diagonals. And then the up diagonals look like this. 1, 2, 3. And what you'll do is you'll multiply down the diagonals, multiply up the diagonals, and then basically just add everything together. Well, sort of add, if you take subtraction to be just a special case of addition. So you take these things, these are going to be positive, add them up, multiply, add all that up, and then take the ones up here, those are going to be negative. You subtract those off. Like I said, if you have a preferred way to do your determinants, you go do it. So let's demonstrate this with a particular matrix. Do I have a particular matrix here? I don't. So I make one up on the fly. That's the beauty of doing math, is I can do whatever I want up here. Let's take that matrix. Where's the matrix? There it is. Let's do the determinant of this matrix. So the determinant of this matrix, to get that determinant, we're going to do take the first column, 1, 1, 5, the second column, 2, negative 1, 7. Notice that I just write them right next to here. It doesn't matter that there's that giant parenthesis there, just ignore it. And then I'm going to draw in my diagonals. These are the down diagonals. I'll try to do it in such a way that I don't obliterate the numbers. Here's the up diagonals. Up, up, up. Now I'll do the calculation. And like I said, for those of you who know how to do this, my apologies, I'll do it. But if you don't know how to do it, if you're confused about any of the steps, please stop me. Otherwise, I'll just barrel on ahead. 1 times negative 1 times 2 is negative 2. 2 times 0 times 5 is 0. 3 times 1 times 7 is 21. Going up now. 5 times negative 1 times 3 is negative 15. 7 times 0 times 1 is 0. 2 times 1 times 2 is 4. Now going back to this, the things going up I'm going to negate. The things going down I leave the way they are. And so my final answer is negative 2 plus 0 plus 21. And then I negate this stuff. It might be easiest to just do a minus here. And then negative 15 plus 0 plus 4. So I've got the stuff going down. Some of them are negative, but that's okay. I add those up, and then I subtract off the stuff going up. My final answer here is going to be, what's this? 36. Oh, I should actually do it, otherwise I'll get it wrong. 21. I've got a bad track record this morning for some reason. There, this is a 4. There. Yeah, that cosine is just ridiculous. Okay, so that's 36 minus 6 is 30. Hopefully I got that right. That's the determinant. And like I said, take linear algebra if you want to know what that determines. Oh, better also, if you take differential equations. This also determines something about a system of differential equations. It determines whether or not there's a solution, the type of solution it has. But for us, we're just using this as a computational tool, kind of like addition or subtraction. This is just a complicated computational tool. Okay, so now we're ready to do the cross product. So the cross product looks like this. Why does it look like that? Because I need to fix, just a minute. I thought I told it to fix all of my equations, but it didn't fix this one. Ooh, interesting. What if I do that? Does that fix it? Oh, it kind of made it weird. I don't know why it made it weird. Well, it almost fixed it. So yeah, for some reason, here, I'll show you what it looks like. Here's Windows, looks like this. The iPad, apparently the font. I don't know if the font is the issue here, but look, yeah, so it's weird that so that's what it should look like. So anyway, if you have two vectors, the determinant of those vectors are what you get when you, the cross product of the two vectors are what you get when you do the determinant of this matrix. We will practice. So let's do this with an example. Yeah, why is the, yeah, okay, here's what we'll do. We'll use Windows, since apparently my iPad doesn't want to render these equations properly. So, so here's an example. Oh, it's all worked out. 1, 1, 1. Okay, let's just back up. We'll go here. This is, whoa. This is the original example. Here it is, the orthogonal, this one. Switch back. This one. So we'll just do this one. Let me get rid of all the pen markings. Okay, so I want to find a vector that's mutually orthogonal to these. And so what I will do is I will do 1, 1, 1 crossed with 1, negative 1, 1. And this will give me, what this will do is you'll have vector 1, vector 2, u or v, and then the resulting vector will be perpendicular to both of them. So you have to imagine that this is sort of, this is three-dimensional, and these are pointing in some different direction. Okay, so so to do this, I do the determinant of this matrix. So you start off with I, j, and k on the top row. Then you put 1, 1, 1 on the second row. That came from here. And then 1, negative 1, 1 is the third row. So there's the start. We're doing the determinant of that matrix. Now, like I said, if you know how to do determinants, or better yet, if you know how to do cross products, you go. But I want to make sure that everyone can do it, including those of you who have not had statics and physics and whatever else you guys use this in every single day. Okay, so the determinant of this, what we're going to do is we're going to augment this matrix with these two columns. So this gets moved over here, and this one gets moved over here. So this is J1, negative 1. So you see that. So we've got our two columns. Now we're going to do our diagonals. And I guess to do that, I better erase my arrows so that I have room. Oh, come on. Erase. Why? Just a minute. Okay. This doesn't make any sense. I don't know why it's behaving the way it is. Okay, now it's doing it. Sometimes I think technology is a little bit, I don't know, gets in the way. So, but we're stuck with it. Okay, there's my up. I don't know why I did the up first. Here's down. There it is. Okay, so let's do this. So let's see, the down diagonals, I have I times 1 is I, j times 1 is j, k times 1 times negative 1 is negative k. Then the up diagonals, 1 times k is k, negative 1 times I is negative I, 1 times j, sorry about that, is j. Now, we'll talk about the I and the j and the k. You probably know what they mean, but just in case, we'll talk about them in a minute. So there's my, my stuff. Now let's go ahead and add this all together. We have I plus j plus negative k. That's the down diagonals. Subtract off the up diagonals. And that's going to give me 2i plus 0j. Notice that the j's cancel, minus 2k. And you could write that like this, 2, 0, negative 2. So for now, this is just, I guess, a vector. It's going to solve some problems for us, though, tomorrow. But for now, it's just a vector. It's just sticking out of the wall, I guess. It's perpendicular to the first two. So, so you have the first two vectors doing something like this. There they are. And then the third vector points out towards you maybe, or maybe away from you, depending on the orientation. We'll get to exactly where it goes in just a minute. But so I have that third vector, the new vector, points perpendicular to both of these. So there it is. That's the cross product. Okay, so let's practice this. and then we'll talk about properties. I know I'm whipping through this, but it's because you guys apparently already know all this. So here's an example. Let's compute. Here we go. More examples. It says more, but yeah. So let's compute these. See if you can do the cross product U crossed with V, and then see if you can do the other one. Go ahead and set it up. Work with your friend if you want to. And I'll clean up here, I guess. I'll do something. Keep myself occupied. Oh yeah, I didn't bring your quizzes because I didn't grade them yesterday, but I'll bring it tomorrow. I'll bring the file folder with all your stuff in it. All right, I'm switching over because it's easier for me to write with this. A sec here. Okay. Paste that in there. There it is. Okay, so I don't know where you are in your calculations, but let me set up U crossed with V just to make sure that we're all on the same page. I will put 1, 3, -4, and then -1, 7, 4, or K, not K, sorry, 1, 1. So one mistake that some students make is when they get down here to this matrix, they'll put I, J, and K in the matrix, but those I, J, and K are just placeholders. They're just there in place of writing this in component notation. So instead of 1, 3, -4, you have I, J, and K. These are sometimes referred to as the standard basis vectors, the unit vectors. But in all, reality, they're just placeholders that are just there to represent the X, Y, and Z components. So they do represent unit vectors, but we don't have to get into that. So you don't want the I, J, and K down here anywhere except for the top row. Same thing here. So there it is. You're going to do the determinant. Let's see if I can do this relatively quickly. So this is going to be 3, 28. Four, that's 3J. And I'll be curious to see if I get this right, trying to do it in my head. 7, 10, 10K. Does that look right? Did anyone do it and get this? I did it? Wow, amazing, incredible. Okay, very good. So we got that. And then the other one, this V crossed with U, some of you know what the answer is going to be without even doing it, but I'll write it out. So just to prove that I did it, give me a sec here. Whoops, I didn't want to do that. Let me undo. I just want the ink. Go down here and paste. And I guess I'm just going to get this. Come on. I can't move it without moving the words. Okay, well, I was just going to cheat and copy this because really it's just switching those two rows. So it's going to be this ijk -1 7 1 1 3 -4. I'm doing the determinant, and I got -31i minus 3j minus 10k. So this probably isn't a surprise to some of you, is that you get exactly the negative of the original when you change the order of the cross product. So this has to do with this physical property of the cross product. So whenever you have two vectors, so here's my two vectors, let's say, and you do the cross product of the vectors, you're going to get another vector that is perpendicular to the two vectors. And so this vector will be perpendicular, but there are two directions it could go. Notice that I could put my new vector pointing this way, or I could put it pointing this way. So either way, it's perpendicular to both of those vectors, pointing up or pointing down. And the way you can tell which direction it's going to go, if you have actual vectors like this, if I did the cross product of the white vector with the black vector here, then the way I figure out which direction this is going to go is I use my right hand. This is the right hand rule. I know you guys, physicists, love your right hand, don't you? So the right hand rule says you take your fingers, point them in the direction of the first vector, so the white vector here, and then curl them in the direction of the black vector, and your thumb will point in the direction of the cross product. So that's the way we'll get. If we did it the opposite, you have the black vector and you want to curl your hand, your fingers, oh, I can't get them to turn. So here, that's a lot easier. Now, black crossed with white gives me the vector that points downward. So that'll be pointing this way. So that's why if you cross product and you change the order, you end up with exactly the same vector, only pointing the complete opposite direction, pointing down instead of up, or left instead of right, or whichever way it goes. All right, so this isn't bad. All right, let's go on to some properties of the cross product, because I know that if you know the cross product, you want to know some fun facts, don't you? So fun facts about the cross product. So number one, u crossed with v is orthogonal, perpendicular to both u and v. Well, we knew this already, though, so that's not very exciting. The next one, u crossed with v is the negative of v crossed with u. Well, that's kind of exciting, but this is the whole business of if you have two vectors and you do the cross product one way, you get one vector. The other way, you get the opposite, but it's completely the opposite, the negative. So not that exciting either. Let's get some exciting things. Well, this is exciting. So the cross product has if you do the magnitude of the cross product, you actually get the magnitude of u times the magnitude of v times the sine of the angle between the vectors. Now, I just want to point out that this is similar in some regards to the dot product. If you did the dot product, u dotted with v is the magnitude of u times the magnitude of v times the cosine of the angle. And that comes from the formula for the cosine of the angle between two vectors. So this is kind of an interesting symmetric equation. That's kind of fun, but it gets better because that's true, and I'm offering these without any proof. So to prove these, you'd actually have to do them in general. It's not that difficult, but I suspect that you don't have the desire to go through the tedium of proving these things. So if you have two vectors that are parallel, so you might wonder what happens if two vectors are parallel, like this, or here, I'll use the white and the black again. So they're pointing the same direction. You could say, well, there are a ton of vectors that are perpendicular to both of these. In particular, any vector that points all the way around here. All of these vectors. And so because of that, the cross product is not unique. And so you'd say, well, the cross product is just 0. So if you have two vectors that are parallel, the cross product is just 0. It's like, because we don't know what vector to use, I guess, that's perpendicular. And this is true this goes both ways. If you get a cross product that's 0, it means that your two vectors that you started with are parallel to one another. Once again, this could be proved, not difficult. This one's easier to prove. And the way you would prove it is you just take two vectors that are multiples of one another, do the cross product, generic vectors like u1, u2, u3, and a times u1, a times u2, and a times u3 for the two vectors. Do the cross product, you get 0 every single time. Okay, finally we get something that's a little bit exciting. And so this actually has to do with this. So these two are related. The second or the third one down and the one that I just put up there, the u crossed with v is the area of the parallelogram, which has u and v as its sides. Let's just pause for a minute and see what this means in terms of an actual set of vectors. So what we'll do is we'll just pick some nice easy vectors, if you don't mind. So I have u equals this. Let's go over 1, up 3, and how about this, 0, so that it's nice and easy. And then v is going to be, how about 5, -1, 0. So both of these vectors exist in the xy plane. So it's like they're like that. They're on the floor or on the table, so they're in the xy plane. The cross product will be pointing either up or down, but we can compute that cross product. So let's compute the cross product of these two. Whenever you have a 0 or two zeros, you should be so excited because it makes the cross product much easier to compute. So let's go ahead and do the determinant of this matrix. And I'll let you do this one, 1, 3, 0, 5, -1, 0. So take a minute, work that one out. You can do it. And I'll find volunteers here. Should have been doing volunteers earlier, but we're going to do it now. We got 13 minutes. Plenty of time. Yeah, so all these zeros, they make things really easy, don't they? Caden, did you complete this? Have you done it already, or are you on your way to doing it? Working on it. So what are the zeros that you're getting? Just about everything, right? Yeah. Like the down diagonals, almost all of them are 0. All right. Well, I'll get here. I'll put in there. I should do it the right way here. Let me write it out, and then I'll find someone to help me out here. I15, J 3, -1. So let's see. We've got this diagonal, this one, and then you got the down diagonals, that one, and that one. Okay, my diagonals are terrible. Hopefully you can track them. Here we go. So Caden, did you want to do any of the diagonals for me? Down or up?
I did it the other way.
Oh, you did it the cool way. You do your way. That's fine. Yeah. Here, I'll find someone else. No, you can do it your way. That's fine. Austin, did you do it this way?
No.
Okay. Yeah, this is like, it's so much easier. Aiken, you did it this way? Yeah. Okay, let's do it. What do you got? Ooh, 0 plus 0 plus -k, right? Okay.
Alpha equals
15k. Yeah, don't forget the k. And then plus 0. Oh, that should be minus all of this, shouldn't it? So I got so excited that I forgot to put the minus in there. So far, so good. So this is going to equal -16k. -16. So just like I said, you've got your two vectors pointing in the plane, the xy plane. And then the third vector is pointing, negative, down. So it must be that you're going like this in terms of these two. But here's the cool thing about this vector is the magnitude of this vector is the same as the area of this parallelogram. So let's see, here's the vector 1. Here's vector, it's going to be u and v. If I were to do this, here's v and here's u. This area will be the same as the magnitude of u crossed with v. So your last chore for this one at least is to compute the magnitude of this vector, 0, 0, negative 16. Some of you probably look at that and say, okay, I can do it without even thinking, but if you need to, you can write something down and we'll get our magnitude. So no matter how you do your cross product, your magnitude will always be the same. So, and those in the cool people, you got this the same thing?
Yeah.
Okay, good. That's fine. All right, Emily, did you get the magnitude of this thing?
It should just be, because there's zeros
Yeah.
and everything else. It's just 16.
Yeah, just 16. Good. Yeah, that's what I meant by like you could write it out like this. Here's the way I'm going to do it. You could say, oh, it's the square root of 0 plus 256, which is just 16. Yeah, it makes sense though. You've got a vector, it's pointing straight down, and it's got, yeah, you're not going left or right, you're just going down 16 units. So why belabor the point? Anyway, that turns out is the area of that parallelogram, which is kind of cool. Now, as long as we have that, before we go on, let me just point out that once you have the area of that parallelogram, you can find the area of this triangle by just splitting that in half. So that area, the area of this triangle, is 1/2 of the magnitude of u crossed with v. So once we have 16, it's like, well, that triangle is going to be area of 8. And I know that the engineers are like, well, why would we care? I don't know. It's beautiful. It's mathematics. Okay, let's go on to the rest of the list, some other cool stuff. So this so-called the triple product here, if you have 3 vectors, here's 3 vectors. So here's my 3 vectors pointing in various directions. Then if you take one of them and do the dot product of the one with the cross product of the other 2, and it doesn't matter which one you choose, then that ends up being the volume of the parallel pipette determined by these 3 vectors. So if you take these 3 vectors and do the same thing that I did with the 2 vectors, make a parallelogram and then take that parallelogram and skew it so that it looks like a box that's been kind of pushed over on its side a bit. That's what a parallel pipette is. It's just a box made up of parallelograms as their sides instead of rectangles. Anyway, that's not all that useful. It's just kind of cool that mathematicians like that. This is the one that's probably the one that you know, the physicists. So this is one of my favorites as well because I think about it every time I ride my bicycle. In particular, here is a picture of not my leg, but I just got this off the internet, of someone pedaling their bicycle. And on this picture, you can see that there are some vectors involved here. And so let's just we'll pretend that this is me. And you have this vector here. That vector is the force. So force is going to be, I am 100 kilograms approximately. And so 100 kilograms, but I have to multiply by 9.8 meters per second squared to get the number of newtons, right? So 9,800 newtons. That's the amount of force that I'm putting on this pedal as I stand on the pedal, going straight down. And then this here, this lever, I'll go back so that you see where this is all going, but I just want to get this drawing up here. So this lever, you could think of that as being a vector, and that vector has a length. So we're going to call that u. U has a length of 0.175. It's 175 millimeters long, my crank arm. Usually it's between 160 and 180 millimeters, our crank arm. So that's in meters because we're going to use meters as our units. Don't worry, I'll put this all up here. So U here The magnitude of u is 0.175. The angle that u makes, whoops, I got to change color to something you can see. This angle, we're going to say, is a 30-degree angle. I know it's probably a little less than that, but we're going to fudge it because we want the numbers to work out relatively nicely. So if that is a 30-degree angle, then we're going to say that this particular crank arm is 0. Oh, we got 5 minutes. We're good. Then 0.175 times the cosine of 30 degrees. Oh, I've run out of room. This is the problem with not having notability. I'll put it on notability. That'll be better. Give me a sec here. Oh, well. Okay, copy. Before we do notability, let me go back and say that what we're going to do is once we have that crank arm vector and you have the force vector cross product with the crank arm vector gives you the torque vector. And the torque, it's always going to go through the axis of rotation, but it tells you how much, torque is measured in force per unit distance. Is that right? Am I thinking of this right? But anyway, we'll get the units in a minute because we're going to do this for this bicycle. So give me a sec. We just track the units. It's one of the techniques that I used to survive physics was I just figured if I could get my units to work out, I'm probably right. I don't know if any of you adopt a similar technique, but if your units work out, then you're probably correct with your answer. So let me rewrite that vector. The vector u here is going to be the vector 0, because notice that the x-axis is the one coming out at you, the y-axis is this direction, the z-axis up and down. I'll write the force vector here in just a minute, but the u vector is 0, and then you have 0.175 times the cosine of 30 degrees, and then 0.175 times the sine of 30 degrees. So here, I know we always think of cosine as being associated with x and sine as y, but here, because the triangle, you've got your y-axis going this way, z-axis going up now, so it got switched a bit. That's my u vector. My f vector is the vector 0, 0, negative 9,800. So that's that force going down.
Yeah, I was gonna say, did you calculate your weight wrong?
Oh, 980. You're right. I'm not an elephant. I have one too many zeros up there. Sorry. Yeah, another evidence that I just need to go back to bed, apparently. But 980 newtons. Thank you. So 980 going down. I would have gotten the right answer just off by a factor of 10. Close enough. Okay. Well, anyway, now to get the torque is u crossed with f. Fortunately for us, there are a lot of zeros here, so this should be relatively easy. So this is going to be, whoops, there's f. So I, j, and k. Give me a sec. I'll get this set up. We have 0.175 times the cosine of 30, and 0.175 times the sine of 30, and this is 0, 0, and negative 980. Well, you can see that, we still have 2 minutes, don't we? Right? Everyone's trying to, yeah, we got 2 minutes, we're good. So you can see here that the diagonals, almost all the diagonals are going to be 0, except for, is that the only one? I think that's the only one that survives of all the diagonals. Or if you guys do it your own way where you segment it off into the little 2x2 matrix, that's fine too. But I think that's the only one that is non-zero when you get done writing all your diagonals in, because the up diagonals are all zeros. And so my cross product, u crossed with f, is just negative 980 times 0.175 times the cosine of 30, which I know some of you are like, well, that's the formula. Yeah, whatever. But anyway, let's go ahead and do this on a calculator so I can evaluate. And that's times I. Hold on a minute. 980 times 0.175 times the cosine of 30, square root of 3 over 2. Okay, I'm getting 148.5. And let me just think through, what are the units? These are newtons. This is a meter, and cosine of 30 has no units, so these are Newton meters, is the amount of torque that's going on this particular lever. This is, if you orient this thing, it's a vector that goes through the spindle of this particular crank arm here. Okay, so your homework, you've got a couple of torque that you're going to do, and one of them compares two different levers. One of them's long, one of them's small. You'll figure it out, hopefully. If not, we'll pick up the pieces tomorrow. And I'm going to stop the recording just in case you want to come and whisper something to me that no one else can hear. Otherwise, hope you have a great day.